Welcome everyone, this is our instrumentation project. We decided to construct a marshmallow cannon which would be used to calculate the relationship between air pressure in a tank with the muzzle velocity upon pressure release. To do this, we took a video at a high frame rate, which we then would take the position relationship between two of the frames to calculate the velocity. This would be useful for anyone using the internet who would like to learn a little more about velocity and frame rates, along with future instrumentation labs and people just wanting to build marshmallow cannons that have certain speeds. The end goal that we had for this project was to be able to measure the velocity based off of the cameras that we had at our disposal. To do this, we also found the uncertainty of this form of calculations and the errors that were associated with them. We began this project, we initially had brainstormed a couple of different ways that we could propel the marshmallows through the air. These consisted of different variables such as gunpowder, gas, spring-loaded, or different types of barrels that could also alter the trajectory of the marshmallow. The choice that we went with a more simple design that would be more within our price range, and it was a little less time constrictive, so we were able to do it in a more timely manner. The reason we didn't go with some of the other choices included they were either dangerous, expensive, or just would take too much time to focus on. Now, Bradley will talk a little more about some of these decisions and why we didn't go with them or why we did go with them.
All right, so our various design decisions were first off for the barrel design. We had the smooth barrel, which just provides a direct path to travel, simple, cheap. It's not great at accuracy over long distances. Then we had the spiral grooved, adds a spin to the marshmallow, which improves accuracy over long distances. It does slightly reduce the velocity by about 5%, which isn't too bad. We also had the ported barrel, which adds vent holes to reduce air pressure behind the marshmallow after it reaches the peak velocity. Its greatest strength is it reduces recoil. It also reduces velocity by about 5% again, and it does require complex manufacturing. Then our alternatives for the air compression mechanism were the electric air compressor. It's great at high pressures, rapidly recharges, very easy to use. It's not great it's not portable, and it does require a power source. Then we had the manual hand pump, very portable, easy to control. It does have a limited maximum pressure, and is very, very hard to pump at high pressures. And then same with the CO2 cartridge system, very easy, portable, consistent pressure deliverage. You only get a few usages per cartridge though, and it is quite costly. And then alternatives to our trigger mechanism, we had the pneumatic switch, which uses the air-operated switch to release compressed air. It does integrate seamlessly with pneumatic systems. It does require very complex setup. Then we have the ball valve, which is just a rotating ball with a hole in it that controls the flow of the air. It's either open or closed, there's no in between. It can withstand high pressures, and the weakness is the lack of flow control. We also have the mechanical spring valve, which releases air by pressing a spring-loaded valve. It's easy to use, it has a built-in automatic pressure relief once the pressure becomes too great for the valve itself. And its weakness is it does wear down quite a bit over time. Now, all those I decided to do a decision matrix, with the 5 being the best choice, the 1 being worst. And it factors in, for instance, the cost. If we are able to grab the part just for free, the cost will be 5. If we have to buy the part and it's costly, it's 1. So for the ones that were the best, we came up with the smooth barrel as the best design, the electric air compressor, and the ball valve as being the best for the decision matrix. The weaknesses such as the pneumatic valve, it's very costly. Its performance is so-so. Obtainability, again, it's costly. Or like, for instance, the ported barrel, its cost isn't that bad, but its performance, it's not needed. We don't really care about the kickback. We're only caring about velocity right now.
Test procedure, we had a 5-step process which included loading the marshmallow into the air cannon, setting the desired pressure on the tank, setting up the camera with the right PSI and lighting, releasing the air pressure so it would hit the marshmallow at a consistent manner, and analyzing the data. Some variables we had during this testing procedure included the precision on the air compressor gauge was not the most precise thing that we could have been using, but it was the highest quality that we had for our budget. Along with that, we also, to limit other variables, we set the marshmallow in the barrel at a consistent depth, making it so it would have the same amount of time to use up what air it had.
The final part of our method section was actually taking these launches and turning into data. So to do this, we took these slow-mo videos that we recorded, and then we would play them frame by frame and measure the distance between consecutive frames. And to do this, we got that distance value, and then we times it by the frame rate and divided it by 12 to get the feet per second for our speed. And as you can see here, we actually got, for each launch, we launch it twice at the same pressure in order to get an average of those two velocities to get a more accurate result, along with the calibration at the very start of our trials as well. And these launches are here on this plot right in front of us. As you can see here, it's the pressure versus muzzle velocity. And we also have our equation there. And with our y equation there, the y will actually give us the velocity, and for x, which is our pressure. Now this is our predictive model that we were hoping to find. And as you can see, by the relative closeness of the data values and the r-squared value, it was relatively accurate. After we have our results, it's important to start our uncertainty analysis. The first part of this was to find the instrument error, the errors in different measurement ways. So there's a couple different ones that introduce a small amount of uncertainty, such as the marshmallow length and diameter, as well as the uncertainty of the frame rate of the camera we used. These were relatively small, so they didn't really have much impact on our measurements. The ones that had more impact were the higher uncertainty, such as air pressure. We did a pressure gauge, which was about plus or minus 1 psi, and the uncertainty of the marshmallow position, which is about plus or minus 0.25 inches due to just the camera quality. And this marshmallow position actually need to be propagated to be able to use in our velocity equation. And if you look at the screen, you can see some of the calculations there, but this ended with the ultimate uncertainty in our velocity of about plus or minus 7.07 feet per second. Okay, for the next part, we wanted to find the uncertainty in our calibration. As stated before, to calibrate our air pressure, we actually shot 5 calibration tests, each at 10 psi. As you can see in Table 1, we have our different velocities with our same pressure, and these can be more visualized in Figure 1 in this plot here. After that, we were able to find the mean of our velocities to be about 98.8 feet per second for 10 psi, and then with some further calculations, we were able to find the simple standard deviation to be 11.94 feet per second. Using these in student T's distribution table, we were able to find a confidence interval for 95% confidence. And this was from about 83.9698 to 113.63. And overall, our uncertainty, as you can see from this, was about plus or minus 14.83 feet per second. Now, this is a relatively, a little bit larger uncertainty than we'd like, but it's obviously not too far off from what we expected. For the next part of our uncertainty analysis was seeing how our predictive model, the linear fit line we had, actually compared to our measured velocity. As you can see in this table here, we have our pressure with our measured velocity and the predicted velocity that we got by plugging in the pressure into the predictive model. After this, we actually found the difference between the two, and then using this difference, we found the mean difference was about 11.8 feet per second, and the standard deviation to be about 9.59 feet per second. And using this in student T's distribution table, we were able to find our confidence interval with about 95% accuracy to 6.7 to about 17 feet per second, with our overall uncertainty being 5.11 feet per second.
This is our goodness of fit, or chi-squared analysis. So the data used for this was the difference between our measured velocity and the predicted velocity from our linear fit model. And so we sorted those data into the 3 bins we came up with, and then using those observed frequencies and expected frequencies found our experimental chi-squared, and you can see that our experimental chi-squared is over here, and it's less than the chi-squared at alpha and nu. And so we can keep our null hypothesis, which was that our linear fit model is accurate at 95% confidence. For the hypothesis testing section of our uncertainty analysis, our null hypothesis was that our max average velocity is greater than 250 feet per second. And because we just wanted the value to be greater than 250, we used our left-tailed rejection model here, and we used our 5 highest velocities to calculate data including average and standard deviation. And it turns out our experimental t-value of 4.172 is greater than our t-alpha value, and so we can keep our null hypothesis, or rather do not reject our null hypothesis and say that our average maximum velocity is not less than 250 feet per second with 99% significance.
So with our marshmallow shooter, we originally expected it to show an exponential relationship between pressure and velocity, and that was our design requirement. However, we ended up with a linear relationship. And the linear relationship has an uncertainty of 5.1109 feet per second between measured velocity and predicted, showing that the shooter did work as it should, which leads me to believe that the shooter did not show an exponential relationship because we just simply did not test at high enough pressures. So in the future, we could have an air compressor that can better test at those high pressures. Ours could not reach a high enough max. We maxed it out about 100 psi. So if we tested at about 120 psi, we should be able to see that exponential relationship. As is right now, though, it does predict a good linear relationship between velocity and pressure, and it can also just be used as a regular marshmallow shooter for fun. And that concludes our project.